Hello, everybody. Today we are here to have a new presentation from Master Denise Mandt from UpNano Corporation from Vienna, Austria, and Master Denise Mandt. She completed her master degree in tissue engineering and regenerative medicine in 2017. She's one of the founders of UpNano and manages marketing and sales of the young high-tech company. As a trained medical engineer in the field of tissue research and regenerative medicine and several years of experience in research, she can advise customers in the biological field and support these customers in the implementation of new ideas. So the topic of her presentation today is whether micro or meso UpNano. So Master Denise, thank you for coming to have here, and it's a great pleasure. Denise is also of Dr. Alexander of Ziankov group in UpNano, and so we would like to know and hear more about 2PP and other technologies you can show us this time. Okay, thank you again.
Thank you very much for the introduction, and I would like to thank you also for having me in this conference setup, and like to tell you more about our company and the technology we are using. So we think that especially high-resolution technologies like the 2PP technology we are using is gaining more and more importance nowadays, as everything is getting smaller and at the same time more powerful. When you think a few years back, we had calendars, cameras, a phone, a computer, and nowadays all these things fit in our smartphone. So throughout our daily life, everything is getting smaller. And especially in medicine and bio applications, there is a lot of demand for these small applications. The technology we are providing is a 2PP based 3D printing system, fulfilling the need of this trend of miniaturization. And when we talk about high-resolution 3D printing, it is not clear which dimension we are talking about. Therefore, we came up with a quite easy idea to picture and to give you an impression of the dimensions. So you basically take a normal pencil and then you sharpen this pencil, and on the tip of this pencil, you can print a whole castle. The castle on a pencil tip, the trademark of our company, UpNano. This castle is 250 micrometer in height, and therefore has all these small details. So you can see the two towers and the right tower, it has even pillars, and one of those pillars has a diameter of 950 nanometers, and thus is approximately 100 times thinner than a human hair. So having high-resolution 3D printing, these really fine and high-defined structures can be realized. When you zoom in, you have these fine pillars, 100 times thinner than a human hair, as I just said, but nevertheless, they fulfill their weight-bearing function, so they still can carry the weight of the tip of this tower. The development of the technology we are using is more than a decade in the meantime. So, and all the development and all the innovations we put into the machine were under the slogan, small, fast, and powerful. So our aim was to not only print small structures and small features, but to also provide customers with a very small and compact printing system. So it has a very small footprint, it fits on every lab bench, it needs no optical table or special equipment. The second thing of the slogan is fast. So as we are a spin-off of the Technical University in Vienna, nevertheless, we have quite a biological background. And our idea was to print with this 2PP technology with living cells. And therefore, the speed and the throughput was key. Our process is up to 100 times faster compared to the market standard so far. And to achieve that, we have to be powerful. Powerful not only as a system as a whole, but also especially for our laser source. We are using a 1 watt laser source, and therefore we can enable these biological applications, but we can also enable mesoscale structures, so very big structures when talking about 2PP technologies. A customer, we offer a solution from one hand. So the Nano One is our key product and all the other things associating around. So we have the software, the user software, which was implemented in-house by our software programmers. It's a standalone software. And then we have the resins. The resins are optimized for the high printing speed. And also we are offering maintenance and know-how, of course, supporting our customers in the implementation of new ideas, project ideas, from the first sketch to the final product, basically. When talking about 2PP, some questions came up. So 2PP is a non-linear process, so a 2-photon process. In the picture, you can see it on the right side. So when using a 2PP process, the material is hardened only in the focal point of the laser beam. So therefore, you can work within the material volume. There is no repetitive material appliance necessary. Different to the stereolithography process you might know, which you can see on the left side. So when you apply the light, the material is hardened along the whole beam. So this is the difference. And therefore, with 2PP process, you can achieve a higher spatial resolution and you can work within the material volume. While printing, the Nano One is black box due to laser safety reasons. But we can have here now with this animation a little insight into the machine. So there are different print modes. This print mode we are looking at now is the bottom-up principle. You can use it for printing in well plates, in microfluidic chips, or other vessels of choice. So you put your material into the vessel, into the well plate, for example. You can see this in this animation in light blue. And then the print job is done layer by layer, starting at the bottom, ending at the top. This printing process is limited to a certain height. As you can see here, when the laser is reaching the top, the laser beam always focuses through a polymer which was already hardened. And this can lead to artifacts and reflections. And therefore, your parts are not true to geometry anymore. But we have a solution for that problem. Another print process is called the wet mode. Using the wet mode, you can achieve, you can print also higher objects. So therefore, in this printing mode, a material reservoir is placed on top of the objective. And then again, the structure is hardened layer by layer. But in comparison to the other mode, here the distance between the laser and the current writing layer stays always the same, and the laser is not focused through the material which is already hardened. Therefore, you can achieve much higher objects. This is possible up to 45 millimeters in height. So this is all covers then basically the whole range, printing from micro to macro objects, and with a height of up to 45 millimeters. We have the different setups depending on the substrates, smaller ones and also bigger ones, and then the corresponding wets to put the material in. The wet has a small thin glass window in the middle. This prevents the contact of the objective and the material you are putting into the wet. and also then preserves the focusing power of the objective. As I just mentioned, we have different glass substrates we are also offering. In addition to the vessels, you can use like well plates, microfluidic chips, petri dishes. These glass slides are intended to be used for the wet mode. We offer here a 1-inch wafer, so a 25 millimeters in diameter, or two different squared glass substrates, one with 20 by 20 millimeters and one with 10 by 10 millimeters. The materials, I already mentioned shortly. We are offering at the moment 3 materials which are optimized for especially the printing speed of the material. We always tend to say the fast process also needs a fast chemistry, so the chemical reaction needs to be induced quite quickly, and also the hardening reaction has to be quick. With the Photo, we are offering a universal performance material. It can print very delicate features and is very suited for the wet mode. The Upsole, this is a sol gel hybrid material consisting of organic and inorganic components. Here we can structure very complex overhanging structures, for example, because this material is intended to, is gel-like at room temperature. So the material is prepared, then the ethanol or the alcohol is evaporated, and then you have a gel-like material where you can print in. And this gel serves as a supporting structure of the structure you're printing. So therefore, very complex overhanging structures, but also structures above each other. So a layer of structures and some material in between and another layer can be produced using this material. Here you also can achieve very fine structures, so sub-micrometer resolution is definitely feasible. And also the material characterization is that it has a very low shrinkage rate. And last but not least, our biomaterial, the biocompatible material, which is especially suitable for bioprinting and biofabrication approaches. This material is a gelatin-based material and hydrogel material with a high water content, so about 80%. This material comes as a kit, so it can be mixed together with a cell culture medium, for example, but when you do real bioprinting, it can also be mixed together with the cell solution, so that the cells are really distributed in the material. And it is especially intended to be used for biological applications and real bioprinting. With these different materials and also with these different wets and everything, we can offer a broad range of possibilities and also sizes. So we can print very meso-scale structures with using a 4x objective. For example, structures like this Eiffel Tower can be realized. It is 40 millimeters in height and has a base of 18 times 18 millimeters and was printed in only 8 hours and 49 seconds. So this was then printed with the wet mode, with the largest substrate with the 20 by 20 square and the large wet. Going down the scale, with the 10x objective, you can print smaller structures, still the same features, just on a smaller scale. And this image should just give you a visualization of what is possible with the different objectives. So when going down the scale, the magnification is increasing and the size of the objects we are printing is basically decreasing. And on the last but not least, we have then the 60x objective. And here we printed a 0.2 millimeter in height Eiffel Tower, so 200 micrometer height Eiffel Tower, which can't be seen anymore with on a normal photo, but which can be seen on a scanning electron microscopic image. And here again, all the small details and the fine features are perfectly fabricated. So with covering this broad scale of applications, we then have, as you have seen in the picture before, these different objectives. So in the standard configuration 3, so with the 10x objective, it's an immersion-free objective with a numerical aperture of 0.4 and has therefore a quite large field of view. Therefore, also stitching is not a problem here. The area you can produce stitching free is quite big. And here it is, this objective is mainly used for macroscopic objects with also microscopic features. Nevertheless, you can also produce fine geometries, like you see it here now on the very right picture. This is a filter-like structure. It's a cylinder with 5 millimeters in diameter and 5 millimeters in height, and channels going through this cylinder, so straight through in different layers. And we have here channels incorporated with 20 by 20 micrometers, 10 micrometers, and even 5 micrometers. So this is a filter structure with very defined pores. And here the accuracy is needed for having these pores, and also for ensuring that the pores are completely open. The second objective, the 20x, here again shown in the example of the Eiffel Tower, is a water immersion objective. It has an intermediate numerical aperture of 0.7, and it is intended for high resolution 3D printing applications. And it can also be used for refractive index matched for hydrogel materials, especially. This one is very suitable. The third one is then the one with the highest numerical aperture of 1.42, and it's in this case an oil immersion objective. It's used for ultra high resolution and feature sizes down to 170 nanometer approximately. And it is suitable for structuring small parts and very complex parts. So with a 60x objective, this is not intended to be used for the cylinders, for example, for printing 5 times 5 millimeters, but really for small micro tags, like you can see on the left side, or surface elements where you have some defined elements on top, and also for grid structures, for example. By covering this broad range of sizes or of scales, we also, the speed is one of the key features to be able to do so. So when printing these very high structures like the Eiffel Tower with 40 millimeters, also the speed of the process has to be in accordance so that it's still economically relevant. And when printing fine structures, even when printing a very complex structure like the castle on the pencil tip we saw before, this structure also has very fine details like the pillars, like the windows or the small steps. But nevertheless, the main material is bulk material, where no resolution is needed. And therefore, one of the key features, which is also patented by UpNano, is the adaptive resolution process. So offering this adaptive resolution, we can distinguish between areas of high resolution, like again, the pillars, windows, stairs, and focus the laser very, very precisely to achieve this fine resolution and these fine features. But when having the bulk material and the inner material, we can enlarge the laser beam by a factor of up to 10. and then write the inner part. We can write the more volume at the same time. So when doing so, when widening up the laser, also the power of the laser is adjusted accordingly, because it's very important for us that we always produce solid structures, so completely solid. We have no supporting grids or shell scaffold approaches here, but also the material properties have to be the same through the whole material or through the whole part. So therefore, when the laser beam is enlarged for the inner areas, also the laser power is adjusted so that the power distribution per square remains the same. This is very important to know that. And the factor, so when widening up the laser, it is just done in Y direction. So the height of the voxel is not affected by the adaptive resolution. And this adaptive resolution then is quite powerful when it comes to the throughput of the machine, as the defined areas of the structures can be chosen individually. So it can happen also for other applications that, for example, you have quite a solid base, like especially for microneedle applications, where you do not need the resolution and where do you not need the tolerances, but at the tips of the needles, for example, the resolution and the fine tolerances are needed, and so therefore also this object can then be separated in two phases basically. So starting with the rough parameters to print the base of this patch, and then switching to the fine and high resolution just to get these tips on top of the bases. As I mentioned before, the throughput increase and the throughput of the Nano 1 system is one of our USPs. And to give you a little, or give you an impression of the numbers, or what we are talking about, I have this example here. It's a spring. It's quite a famous benchmarking part in 2PP. I don't know why exactly, but it's a functional micro part, so the spring can actually spring. And a competitor was showing exactly the spring with a height of 6 millimeters on his webpage, and stating that it was printed in 2 hours and 43 minutes. And exactly the same spring, also functional, which can also spring, was printed with the Nano 1 machine in only 5 minutes and 30 seconds. So the advantage in speed is really significant. And this advantage of throughput is not only this adaptive resolution, because this is not really affecting in case of the spring, because there is just a very, very fragile structure. But it is an interplay of different things. It is hardware, it is software, it is also the chemistry behind. So therefore, the USB is a mix-up of very different things. And coming back to the software, for us it was very important to have just one software package for the customer, where he can implement all the features and the parameters. So with the system, it is, for example, possible to place different STL files within one job, and also to give the different parts different parameter settings. So you can, for example, create an array where the density, where the printing power or the speed is increasing each row, and therefore you can make an array with different settings and compare it then during your evaluation. But the second USB besides the speed is, of course, the potential for biological applications. So, as I said before, with our background from the Technical University, with these biological applications, it was always our goal to enable this high-resolution bioprinting, and therefore the whole system was designed and developed with these biological applications in mind. The Nano One as a desktop system can be equipped, for example, with a incubation system. So when you have the door, there is a little hole or a gate where the tubings and cables of the incubation system can be passed through, and then the temperature, the humidity, and the CO2 level of the environment can be controlled during the whole printing process, and therefore supporting the native environment or mimicking the native environment of the cells and supporting the viability. So there are different stages of biological applications. We, for example, can of course produce cell scaffolds. So this is not a true bioprinting application, because you basically just produce the cages, and the cells are then combined in the second step together with these cages to end up with cell balls. These balls can again be fused, for example, to have a big agglomerate of cells and cell cages, which can be implemented, for example, in a defect area, to having the cell power and also then the support of the scaffold structure, so that they on the one hand side have a mechanical stabilization, and on the other side that they stay on the position they are intended to stay. This can be done in different vessels and configurations. Our goal was here to be very open and very flexible. So, for example, with the right insert, you can use cell culture plates, for example. The cell culture plate has to have a glass bottom with a 170 micrometer thick glass, because all the objectives are corrected to this 170 micrometer glasses. And then the scaffolds can be produced in the bottom-up approach we saw before. So beginning at the bottom and ending at the top. Here again, you can see it, and one of these cages be printed. Here you can print an array of cages at the same time. So the maximum we are printing now is above 300 of these scaffolds on the 20 by 20 substrates. Or you can, for example, use a 96 well plate and place one of these cages in each individual well. So there is a software interface where you can put the STL files basically in the individual wells. And also the parameters of these printed objects, so of the cages in that case, can be varied from well to well. Also for us, it was important that the system is equipped with a HEPA filter system. So we have a filtered airstream above the building platform, which prevents the contamination, for example, with dust, as dust particles are often bigger than the structures we are actually printing. When the system is open, we have clean room conditions of 1000, and when it's closed, you have no particles, and we fulfill clean room 100 requirements. The HEPA filter is on the whole time, so while printing and also when opening up the system, and therefore ensures that everything is clean. This approach is, for example, done with the Upsole material, this organic and inorganic hybrid material we are offering. The next possibility with biological applications would then be the real bioprinting approaches we're calling it. So really embedding the cells into the material. This is done then with the Biomaterial. This is a material which came as a kit, as I said before. So you prepare the cell solution with the cells of choice, then mix it together with our monomer and the photoinitiator, and then the cells are really distributed in this material. And when printing, the material is hardened and the cells are then therefore embedded in the structure. And after the printing process, the remaining cells can be washed away. When doing bioprinting approaches, we strongly recommend to use the incubation module or the biomodule, so that you have the stage stop incubation system where the CO2, the humidity, and the temperature can be adjusted and controlled during the printing process. And Alexander Ovsyanikov and his group have shown several times already that with this setup and these materials, you can achieve really high resolution 3D printing approaches and realizing them. Yeah. With the setup we are using, it is possible to print within the vessel. This is true for bioprinting. This was also true for the scaffold approaches. So you basically prepare your material under sterile conditions. You can do that in a laminar flow hood, put the material into the vessel of choice, a well plate, a petri dish, whatever you would like to. And then you can close and seal this vessel, transfer it to the printing system, enter the vessel, print within this vessel, and after the print job has finished, then you can take the sample out and reopening it just under the laminar hood. So the material and or the cells are never exposed to the environment during the printing, and all the preparation and post-processing of the material can be done under the laminar hood to ensure the sterility of the scaffolds or the whole samples. Yeah. And last but not least, another option of printing is, of course, also within special vessels, let's say like that. For example, a microfluidic chip. So this can be either a custom-made microfluidic chip or a commercial one. There are a lot of manufacturers offering these plastic microfluidic chip models where you just apply a sticky slide, again with 170 micrometers on the bottom, so that you have again this thin glass where the objective can be focused through. And when doing customized microfluidic chips like this, you can see here, this is a model from my master's thesis. So the outer microfluidic chip, so this X shape, was casted with a PEG DMA, and then the membrane you can see in the detail image at the top. This was then printed with the 2PP setup, and this membrane is a semi-permeable membrane printed with the Biomaterial. And by choosing the hedge and the layer and the line distances, you can also influence, for example, the porosity or the permeability of this membrane. In this case, it was meant to be a placental model. So modeling on the one hand side the fetal side, and on the other side the mother side, and having exactly this membrane separating the fetus and the mother, and having also the semi-permeability. So it is permeable, for example, to sugar and nutrients, but it also ensures at the same time that the cells you're applying to this membrane stay exclusively on the one or the other side. So after fabrication, the different compartments were seeded with cells, so umbilical cord cells and endothelial cells, and all this again was done in a sterile environment. So already the PEC DMA casting of the chip was done under the laminar hood, and also all the preparations of the material were done under sterile conditions. Then the material was washed away and the cells were seeded. Also, pretreatments of the chip or the materials are possible to have a better adherence, for example, cell adherence. All this can be done again in sterile conditions and also after the printing process. While printing, as I mentioned before, there is no repetitive material appliance, so all the material needed for the whole printing process is already there, either in your well, in your microfluidic chip, or in the vat you place on top of your objective. So therefore, the microfluidic chip is an ideal setup to do so. And when printing, you can then do separators, you can do some channel structures, or like in this case, the membranes. But you can also, of course, use some mixing elements. These structures can be defined individually. It's important just to make sure that at the end of the printing process, the remaining material can be removed again. So when printing circular structures from the top to the bottom of the whole chip, then the middle part is not development, as you cannot develop the structure anymore. So therefore, you always have to make sure that you can apply after the printing process a certain flow to wash away the unpolymerized material. As I said before, the whole setup is very modular, so it was important, or is important for us to give the customer freedom, experimental freedom, so that he can or she can use different substrates, like I said before, the petri dish, and also microslides, for example, and to adapt the system to the individual need. So the building platform of the Nano One system is basically an inverted microscopic stage. So the standard inserts can be used, and therefore also can be adapted to the needs or to the platforms of choice. Then, yeah. When finishing the print job, there is no post-treatment necessary, so no UV post-curing or things like that have to be done. The only thing which you have to wash away the not polymerized material, so the unpolymerized material, and this is done by an alcohol-based solution. In most cases, it's an isopropanol-based solution that is used to wash it away. And then the structures can be used and further processed. When printing on the substrates I showed before, so on these glass substrates, there are different options. So you can either pre-treat them with a silan solution to ensure that the parts stay bounded to the glass substrates, or you can also, when they are very fragile and you would like to put them down again from these substrates, also this silanization process can be skipped, so then the adherence between the material and the glass substrates is not that strong, and the material and the structures can be removed easily. This is then depending on the further use of the structures, and depending on what would be the final use. When doing the bottom-up approach, so when printing within a vessel, also different pre-treatments can be done. Of course, with the vessels like the well plates, you can also pre-treat them to get a better adherence if this is necessary, or if this is something supporting the further processing, or you can just have it like it is without pre-processing for structuring, and then also for easier detachment. The only thing when printing to consider when printing inside a vessel is that it is important to print with a glass bottom, so either on a well plate with a glass bottom, or a microfluidic chip with this glass bottom, like we said before. To end this presentation, I would like to show you a short video quickly. I just have to quickly change the screen. 1 second. It is a video of the Nano 1 printing system to again give you a better understanding and an idea of the things we just talked about. So the video just gives you an overview of where the machine can be placed and how a potential setup look like, and also just visualizing the different steps of the process. And when my foil C player is doing what he's intended to do, you will see the video in a second. Yeah. In the meantime, again, I can summarize the key features. So there is no vibration isolation, for example, needed. So you can basically place it on a normal lab bench and having it there. So it's very small in its footprint. Also, we have it. Okay. At the moment you can't see the video, I think, because now you can. So you can see here that it is very clean in its design. So we just have two buttons on the machine, opening up. All the objectives are labeled with barcodes, so that the system and the software can counter-check, so whether the right objective is set in the software corresponding with the objective which is insert. Then you can click in the stage, very individual, and then again place the bed on top of it. And what we have seen before, this glass substrates then can be fixed in. The materials, we have this UpPhoto and the Upsole I mentioned. They coming in brown glasses bottles, and the UpBio then as a kit, and they can be applied on top of this material bed. And it's ensured that there's always enough material for the whole printing process. So the substrate size corresponds to the material volume you can apply. And all the other parameters and all the definement of the print job is then done via the software. So there is no interaction with the system necessary. While printing, you have two cameras, so one going through the objective so that you can see the current print layer. And there is a second camera system looking from above so that you have a picture of the building platform while you're printing, but this is especially necessary for alignment. And after the print job, the remaining material, or the material which is not polymerized, is washed away. And then the structures can be further processed or just imaged under a normal microscope for bigger and mesoscale structures, or under the scanning electron microscope for the very small structures. I hope that it was a good overview of all the possibilities which can be done done with the Nano 1 printing system. So it's a very, there are very different possibilities you can do. So starting really from bio applications in the medical field up to also then some tags or filter structures, then ending up basically with some cell and tissue applications where we really embed the cells into the printing material. So with the UpNano or with the Nano 1 system, it's opening up a universe of applications basically. And with that, I would like to thank you for your attention. And yeah, thank you for having me today.
Okay, dear Denise, thank you so much for your nice presentation. It's we can see that this 2PP technology, it's very powerful, and this can it's already helping bioprinting area, but I think this we have many challenges to be addressed, and I think everyone is who is attending this lecture will be very interested to know more about this technology, and I invite them everyone to visit UpNano website and address some questions. Okay. By now, I would like again to thank you for participating and to give us more details about this rich technology. So.
Thank you very much.
Okay, so I hope we can have you in other opportunities. Okay.
Of course, very welcome.
Thank you, Denise.
Thank you for having me today. Thank you.
Bye bye.
Bye.